Okay, so as I said last week, you guys do have a quiz today, but we're going to get started on the next chapter, polynomial functions. Quiz is only one page, two sides, so it's not long, but you should have at least a half hour to write it, and if you need a bit more time going into lunch, then you'll be able to do that as well. So, this is the third chapter of Unit 1. After this chapter, you'll be writing your first big unit exam. You only have 4 of them to write in this course. So when we're done this chapter, it'll be the first unit exam. So we're going to learn about polynomial functions. So some of the key terms we'll talk about. What is a polynomial function? We'll talk about the end behavior of these polynomial functions. We'll learn about synthetic division, remainder theorem, factor theorem, integral zero theorem, and what the multiplicity of a zero means. So those are all the different things that we learned about in this chapter. So in this first lesson, we'll identify polynomial functions and analyze them as well. So on the previous page, we talked about end behavior. That is the behavior of the y values of a function as the absolute value of x becomes very large. So another way of saying that is as x gets really, really big, in other words, as the graph goes to the right forever, what is it doing? Also, what happens when x gets really, really small? As the graph goes to the left forever, what is the graph doing? You're going to see that it's either going to be rising or falling. So we're going to talk about the end behavior in terms of rising to the left or falling to the left, rising to the right or falling to the right. These polynomial functions will do 2 of those. What's it doing as you go to the left forever? What's it doing as you go to the right forever? Okay? So we're going to talk about the end behavior. We're going to talk about the degree of the function and what it means. We're going to talk about the constant term. What does it tell you? What does the leading coefficient tell us? As well as the number of x-intercepts. So at the end of this chapter, when you look at an equation of a polynomial function, you're going to be looking at those main characteristics, and it's going to tell you pretty much everything you know about what you need to know about what that graph looks like. So those are all the things that we're going to be talking about to help us have an idea of what the graph will look like. And we'll be able to draw a fairly accurate sketch using those characteristics. So on the right, what is a polynomial function? It is a function of the form. And so that's a long kind of general form of a polynomial function. But basically, it is a function that has a power. Okay? Now, when you look at this, n represents or is tied to the exponent on the variable x. So that first term is a. The a represents the coefficient, a sub n, x to the n. That's the first term. So n refers to the power. And if you look at what it says down below here, it says that n has to be a whole number. So in order for it to be a polynomial function, the exponent has to be a whole number. It can't be a fraction. It can't be a variable. Okay? And we'll see some other examples of different n values that will make a function not a polynomial function. So x is a variable. The coefficients are a sub n through a sub 0, and they must be real numbers. So no imaginary numbers. An example of an imaginary number would be the root of a negative. Okay? So some examples of polynomial functions are 2x minus 1, or x squared plus x take away 6, or x cubed plus 2x squared minus 5x minus 6. In every case, the exponents are whole numbers and the coefficients are real numbers. The degree of a polynomial function in one variable x is n, the power on the initial term. The highest power is the degree. Now, they're not always written in order from highest power to lower. That's usually the way they're written, but not always. So you always want to check to make sure. Just do a quick scan of all the terms, but the highest power will be the degree of the polynomial function. The coefficient of the greatest power of x is the leading coefficient. And again, that's going to tell us something very important about the graph. And the term whose value is not affected by the variable because it doesn't have an x in it is the constant term, a sub 0. And again, that's going to tell us something very important about the graph. So in this chapter, the coefficients a sub n to a sub 1 and the constant a sub 0 will be restricted to integral values, meaning they are integers. Okay? So the first example, identifying polynomial functions. Which of these are polynomials? Justify your answer. If it is a polynomial, we'll state the degree, the leading coefficient, and the constant term of each. So the first one is not a polynomial function. That's a radical function. The square root of x is the same thing as x to the 1/2. Remember we said that in order for it to be a polynomial function, the degree or the power must belong to the set of whole numbers. This is a rational number, power 1/2. So this is not a polynomial function because of the exponent 1/2. The second one, though, is a polynomial function because the coefficient is a real number and the exponent, the power 4, is a whole number. So when it is a real polynomial function, we're asked to state the degree, which is the highest power. In this case, there's only one power, so that power is the highest power. So the degree is 4. Leading coefficient, that is the number in front of the highest power term. Again, in this case, there's only one term, so it can only be 3 for our leading coefficient. And the constant term would be 0. If you put a plus 0 on the end, that doesn't change the value of that function. So the constant here will be just 0. Question C is not a real polynomial function. This is an absolute value function. You actually cannot write the absolute value of x in another form, like x to some power. It just doesn't exist. So this is an absolute value function, which we saw before in the previous 2 chapters. It's not a polynomial function. Right? But question D is a polynomial function because all the coefficients are real numbers and all the exponents are whole numbers. So therefore it has a degree, which again is the highest power. This one is written in order of descending power. The highest degree is 3, so that is the degree. Our leading coefficient will be the coefficient in front of that term with the highest power, that's 2. And our constant, in this case, would be -1. There's the constant term. Okay? So we can do the same thing for the ones below. That first one, 1 over x is the same as x to the -1. So therefore it's not a polynomial function because the exponent is not a whole number. It is an integer. Question B, though, would be a polynomial function because all the coefficients are real, all the exponents are whole numbers. The one thing you want to make sure, though, is that to get the degree, you make sure you pick out what the highest power is, which in this case is in the second term. That would be a power 5. So therefore, our leading coefficient is the coefficient of that highest power term, which in this case is -2, and our constant term would be +3. C is also an example of a polynomial function. All the coefficients are real. All the exponents are whole numbers. This one is in the proper order, highest power to lowest power. The degree would be 4. The leading coefficient would be -4, and our constant term, whoops, for B I said the constant was 3, it should be 4, so let's fix that. Looking at the wrong one, I'm going to pick that out. But everything else for part B is correct. And D would not be a real polynomial function because the exponent is an integer. So we can say the exponent is an element of I for integers. Remember, the exponents have to be whole numbers. All right. So, what are the characteristics of a polynomial function? So, these functions and graphs can be analyzing by identifying the degree, the end behavior, the domain and range, and the number of x-intercepts. Just took a slip, trips, and fall course, and this would definitely be one of those. It's fine, don't spend it, it's fine. Okay, so again, by looking at the equation, you're going to be able to determine what these characteristics are. All right, so first, if the degree is 0, that's a constant function. That's an equation that has no power, or if it did have a power, it would be x to the power 0. It would be a degree 0. That is a horizontal line. So that is the line y equals 3. And note, the degree is considered to be an even number because it's a degree of 0. And there are no x-intercepts. This graph does not cross the x-axis. Okay? So we might see a few of these pop up from time to time, but we're going to be focusing on degree 3 and 4 polynomials in this course. Okay? It does talk about degree 5. That's not part of this curriculum, but we're going to see some patterns developing here. So let's talk about a linear function, which is a degree 1. So that degree is an odd number. And note that there is one x-intercept. So the end behavior of this graph is that it would fall to the left and rise to the right. Now they talk about extending down into quadrant 3 and up into quadrant 1. I'm just going to simplify things by saying it falls to the left and rises to the right. Okay? This line has a positive slope. And remember what y equals mx plus b tells us about a line? It tells us a slope in the y-intercept. If you have a linear function and it's written in y equals mx plus b, meaning you got y by itself on one side. On the other side, normally there are two terms, one term that has the x, one term that is a constant. The term that tells you the x tells you the slope, right? It's the number in front of x. The constant tells you the y-intercept. So in this case here, because the leading coefficient is a positive value, that means it has a positive slope. That means it'll fall to the left and rise to the right. When the slope is negative, the opposite happens. That means it's going to rise to the left and fall to the right. So that's what we're looking at when the degree is 1, which is an odd number. The next one is an example of a quadratic function. You looked at quadratic functions in 20-1. Those are degree 2 functions. The degree is an even number. And this graph rises to the left and rises to the right. If the initial term coefficient was negative, like this one is positive 2, that's the initial term coefficient. And you remember from 20-1, when the number in front of the x squared is positive, that tells you it opens upwards. It'll rise to the left, rise to the right. If, however, that initial term coefficient is negative, the graph has reflected over the x-axis. Now it opens downwards, and it's going to fall to the left and fall to the right. So when the degree is 2, which is an even number, and the initial term is positive, then it's going to open up. But when the initial term coefficient is negative, it'll open down. And again, that's a second degree polynomial. The next one is an example of a cubic function. Okay? A cubic function. So in this case here, the initial term coefficient is positive 1. This graph falls to the left, rises to the right. This is a cubic function, which is an odd degree. So it's actually acting just like a line with a positive initial term coefficient. When the line, a linear function, has a positive initial term coefficient, the graph falls to the left, rises to the right. That's a degree 1, which is an odd number. This is a degree 3, though, which is also an odd number. But the same thing happens. When the initial term coefficient is positive, it falls to the left and rises to the right, just like a line with a positive initial term coefficient. If the initial term coefficient turned to negative, that would reflect the graph over the x-axis, right? And that means it would rise to the left and fall to the right, just like a line with a negative slope. It rises to the left, falls to the right. So there's a connection between linear functions and cubic functions. The end behavior will be the same based on whether the initial term coefficient is positive or negative. And when we look at the quartic function, that's a fourth degree, again, it's going to work the same as a quadratic. Both of them have an even degree. A quadratic is a degree 2, a quartic is a degree 4. They're both even. When a quadratic has a positive initial term coefficient, it opens up. When the initial term coefficient is negative, it opens down. Same thing with fourth degree polynomials. In this example, the initial term coefficient is positive 1. So it rises to the left, rises to the right, just like a quadratic with a positive initial term coefficient. If we change the initial term coefficient to negative, again, that would be a negative a value. The graph would be reflected over the x-axis, and the graph would now fall to the left and fall to the right. So it acts the same as a quadratic. So the degree and the initial term coefficient will tell you the end behavior of the graph. Just by looking at the degree and the end behavior, the degree and the initial term coefficient, it'll tell you what the end behavior of the graph will be. Right? Now, let's go back. When we talked about the line, that's the graph of y equals 2x plus 1. That's a degree of 1, and note that there is one x-intercept. If you look at the second one, a quadratic function, in that case there, that's a degree 2, and notice that there are two x-intercepts. You might remember, though, that when you looked at quadratics in 20-1, there were also some examples where there were no x-intercepts. If this graph was shifted up, let's say 4 units, it wouldn't cross the x-axis, so there'd be no x-intercepts. If it was shifted up 3 units, it would touch the coordinate plane at the point 0, 0. It would look like basically the graph is bouncing off the x-axis at the origin, and there's only one x-intercept. But because the degree is 2, the maximum number of x-intercepts it could have would be 2. Okay? When we look at the cubic function, that's a degree 3, and note there are 3 x-intercepts. And that's the maximum number of x-intercepts this could have. If you shift this shift this graph up, let's say 1 unit, it would still have 3 x-intercepts. But if you shifted it up, let's say 3 units, now it would only have 1 x-intercept. But the maximum number of x-intercepts it could have is 3, which is the degree. So this is the pattern we're seeing now. The degree will tell you the maximum number of x-intercepts. Same thing with the quartic, the 4th degree. Looking at that graph there, it has 4 x-intercepts. You could shift it down a couple units, and then it would only have 2 x-intercepts, but the maximum number it would have would be 4. So the degree will tell us the maximum number of x-intercepts. Finally, the constant term tells us the y-intercept. In the case of the linear function, y equals 2x plus 1, m is the slope, that's 2, b is the y-intercept, that's positive 1. Same thing with the quadratic, right? The constant term there is negative 3, that's the y-intercept. When we look at the 3rd degree polynomial, the constant term is negative 2, that's the y-intercept. Remember, the y-intercept is always where x equals 0. If you let x equal 0 in any equation, all the terms that have x will become 0. You're just left with the constant term. Same thing with the 4th degree, right? That constant term for that one is negative 6. And again, that is the y-intercept. So that's what the constant term tells us. It tells us the y-intercept. So by looking at the equation, you can look at the degree. It'll tell you the number or the maximum number of x-intercepts the graph would have. Also, that along with the initial term coefficient tells us the end behavior. When the degree is 3, which is an odd number, compare it to a line. When the initial term coefficient is positive, it'll fall to the left, rise to the right. If the degree is 4, which is an even number, compare it to a quadratic. If the initial term coefficient is positive, it'll open up. It'll rise left, rise right. If it's negative, though, it'll open down. It'll fall left and fall right. So that first term tells us a lot about a polynomial function. And then if you look at the constant term, that will tell you where the y-intercept is. So we can use all these characteristics to help us sketch a fairly accurate graph. So on this example, it says match a polynomial function with its graph. Identify the following characteristics of the graph of each. The type of function, whether it's even or odd, the end behavior, the number of possible x-intercepts, whether the graph will have a max or min value, as well the y-intercept. Then match each graph to its corresponding, each function, I should say, to its corresponding graph. So looking at that first function, negative x to the 4th is the initial term. It's written in the proper order, highest power to lowest. The degree of that is 4, which is an even number. So we're going to compare it to a quadratic. The initial term coefficient is negative, which means looks like a quadratic with a negative initial term coefficient. It's going to open down. So it's going to fall to the left and fall to the right. So we can eliminate graph A, we can eliminate graph B, and we can eliminate graph C. The only one it could be is graph D. That's the only one that falls to the left and falls to the right. Also, when we look at the equation, the y-intercept is negative 4. And even though there's no scale on the graph, the y-intercept on graph D is definitely negative. It's below the x-axis, right? So graph D matches equation A, or equation A matches graph D. So again, when we talk about the characteristics for equation A, it's an even function, or quartic in this case. That graph falls left and falls right. So we can say it falls left and right. There's a maximum of 4 x-intercepts And this graph does have a maximum point, and you can see it. There is a maximum point on this graph, but there is no minimum point because the graph falls to the left and falls to the right. It goes down forever. So it never reaches a low point. It just keeps going down. And the y-intercept is at -4 because that's the constant term. All right? Looking at graph or equation B, that is a third degree polynomial. So it's going to act just like a line because the degree is odd. The initial term coefficient is +1. So it's going to act just like a line with a positive slope. It's going to fall to the left and fall to the right. The only graph that we have left that falls to the left, and I think I said falls to the right. That's not correct. It's got to fall to the left and rise to the right because it acts just like a line with a positive slope, which is what graph A does. Or graph A matches equation B. This is a cubic polynomial, which is an odd degree. And again, because the initial term coefficient is positive, this graph will fall left and rises right. Because it's a third degree polynomial, there will be a maximum of 3 x-intercepts. And because it falls to the left and rises to the right, there is no max or min value. And the y-intercept, remember, is the same as the constant term, which would be +3. That's our constant term. Looking at equation C, that would be a fifth degree polynomial. Now again, that's not really part of the curriculum. However, because the degree is odd, we go back and compare it to a line. Okay? The initial term coefficient here is negative, which means it's going to act just like a line with a negative slope. It must rise left and fall right, which is graph C. Or equation C matches graph C. So again, this is known as a quintic. The degree is 5. And once again, because the initial term coefficient is negative, this graph will rise to the left and fall to the right. Because it's a fifth degree polynomial, there would be a maximum of 5 x-intercepts. And we talked about the fact that a quadratic is possible for it to have no x-intercepts. It's also possible for a fourth degree polynomial to have no x-intercepts. But if the degree is odd, it will always have at least one x-intercept. At least one. Okay? A line will have at least one. A third degree polynomial will have at least one x-intercept. And anytime the degree is odd, it will have at least one. But when the degree is even, it's possible for there to be no x-intercepts. So again, because the degree is odd, because it rises left and falls right, again, there will be no max or min value here. And the y-intercept equals the constant term, which in this case is 0. There is no number at the end without an x. If you add a plus 0 on the end, you haven't changed the function in any way. So here our y-intercept would be at 0. This graph would go through the origin. All right, so we're just left with equation D, which would match graph B. That is a fourth degree polynomial function. That degree is even, so it's going to act just like a quadratic. The initial term coefficient is positive 1, so it'll act just like a quadratic with a positive initial term coefficient. It will rise to the left, rise to the right. So again, this would be graph B, or graph B matches equation D. This is a fourth degree polynomial. Or a quartic again. And once again, because the initial term coefficient was positive, this graph rise to the left and rise to the right. It opens up. Because it's a fourth degree polynomial, there would be a maximum of 4 x-intercepts. But it's possible that you could have a fourth degree polynomial with no x-intercepts. This graph could be shifted up far enough so it never crosses the x-axis. There is a minimum point on this graph. And again, the y-intercept is the same as the constant term, which in this case is negative 12. And you can clearly see, looking at the graph, that the y-intercept is negative. In this case, it's negative 12. Now, this graph is not drawn to scale because they have a value of negative 30 at the bottom. That should be much further away from negative 12, but it's not drawn to scale. And you can always put these in your graphing calculator as well when you have the equation. See what it looks like. It'll graph it for you. So, describe the end behavior of the graph of the function negative x cubed minus 3x squared plus 2x plus 1. So that is a third degree polynomial, which is an odd number. So compare it to a line. The initial term coefficient is negative, which means it would act just like a line with a negative slope. It would have to rise to the left and fall to the right. We know that by looking at the degree, seeing whether it's odd or even, and then comparing it to either a line or a quadratic, along with the initial term coefficient. So therefore, it's a third degree polynomial, which means we'll have a maximum of 3 x-intercepts. Again, the degree tells us that. The y-intercept would be, again, the constant term, positive 1. And because it's a third degree polynomial, again, 3 is an odd number, it would act just like a line. It's going to have at least 1 x-intercept, but a maximum of 3. Also, it means that it's not going to have a max or min value because it rises one way to the left and falls to the right. There is no max or min. So, we're looking for a graph that rises left and falls right. So that eliminates graph C and D. They both fall left and rise right, so that's going the wrong way. And if we look at the two graphs, a couple differences are, two graphs we have left, I should say, a couple differences are the number of x-intercepts, but remember it's possible for an odd degree to only have one x-intercept, so that doesn't help us. But what is also different about these two graphs is where the y-intercept is. In graph A, the y-intercept is below the x-axis, which means it's negative. In graph C, it's above the x-axis, which means it's positive. And in this case, the y-intercept must be positive 1. So that makes graph C our answer. It has the correct y-intercept as well as the other correct characteristics. Okay? A bank vault is built in the shape of a rectangular prism. Its volume V is related to the width W in meters of the vault doorway by this function. What is the volume in cubic meters of the vault if the door is 1 meter wide? So for question A, we're going to find V at 1. W represents the width of the doorway, and the function will tell you the volume of the vault. So in this case, we're going to determine the volume when W is 1. So, I mean, all those terms are just going to become whatever their initial term coefficient is. It's going to be 1 plus 13 plus 54 plus 72. And if you add those together, you'll get 140, and that would be cubic meters. Now, part B says, what is the least volume of the vault? What is the width of the door for this volume, and why is it not realistic? So when you look at the scenario we're dealing with, you would realize that the width can't be negative, because you can't have the width of the door being negative, all right? And the volume can't be negative either. If we look at the graph of this function in our calculator, so we can only have variable x in our calculator, even though the equation has variable w, it doesn't matter. So I've got x cubed plus 13x squared plus 54x plus 72. So I put that equation in there. And if you just hit graph now, you may or may not see any part of the graph. It depends what the windows are. But remember, we can only have positive values of W and only positive values of volume, right? If we look at the graph right there, I only see negative values of W. That graph is to the left of the y-axis. I need to see positive values of W. We know by looking at the equation that the y-intercept is 72. So this graph, because it's a third degree polynomial, it's going to keep rising to the right. It'll go through the y-axis at 72, and then it'll keep rising after that. However, that's where the graph is going to cross the y-axis. That's where it's going to go from negative values of W to positive values of W. So what does that mean? Well, it means that our windows, our y max, has to be at least 72. So I'm going to change it to, let's say, 120, and I'm going to set my y scale to 10. So now I'll be able to see where the graph crosses the y-axis, which will be where the W values change from being negative to positive. So again, this graph represents the volume. Okay, it represents the volume. And the volume has to be positive. According to this graph, the minimum volume will be actually, when W equals 0, and with that equation, the volume would be 72 cubic meters, because that's the y-intercept, the point 0, comma 72. But that's not really going to work, because remember, W represents the width of the door, and if you have the width of the door being 0 meters, you got no door. And so that's why it says, why is this situation not realistic? So again, the graph tells us that the minimum volume will equal 72 meters cubed, which occurs when W equals 0, the width. And this is not realistic because there is no door. Okay? And the next question is really the same thing, so I'm not going to spend any time doing it. Now, going back, I want to talk about one more characteristic before we leave this. Look at the degree 1 polynomial linear function. That graph never changes direction. I mean, that's what a definition of a line is, right? It goes at a constant slope. It never changes direction. It has 0 direction changes, and the degree is 1. Looking at the quadratic has 1 direction change. It occurs at, in this case, the minimum point. So a quadratic will have 1 direction change, and the degree is 2. Looking at the cubic function, that graph has 2 direction changes. It has what's known as a local maximum point right there and the local minimum point right there. That's where the graph changes direction. This graph has 2 direction changes, and the degree is 3. There's a pattern here. The number of direction changes is always 1 less than the degree. With the 4th degree polynomial, it should have 3 direction changes, and it does. There's the first, there's the second, there's the third. The number of direction changes is always 1 less than the degree. And the same thing works with the 5th degree polynomial. That should have 4 direction changes, and there are 1, 2, 3, 4 direction changes. So that's another characteristic that we can add to our list. The number of direction changes is always 1 less than the degree. So there will be some cases where that would help you identify what graph matches what equation. All right, so I'm going to stop there. I'll put some questions up here for you to work on. Hopefully you can find the time to work on these questions. I will post the solutions to Google Classroom so you can check your answers. Like I said, hopefully you can find the time to do that.